This is the second video of a series on vectors. The first video introduced vectors in two dimensions, looked at the vectors written in component form and at the magnitude of the vectors. So in component form, the vector was given as an x component and a y component, where if you're moving from one end of the vector to the other, you move a certain number of units horizontally in the x direction and a number of units vertically in the y direction. Given as a column vector here, A is the x component, B is the y component. And the magnitude of the vector followed from Pythagoras' theorem that the size of the vector, how long this line is given by Pythagoras' theorem. So we square the components, add and take the square root to get the size of the vector. So that was in the first video. This video continues with vectors in two dimensions, but it's looking at adding and subtracting vectors, both by diagram and using components, and also multiples of a vector. First, a reminder of component form from the previous video. So this vector A, if you start at this point here and move along the vector to the end of the vector, in terms of x and y direction, you've moved 2 boxes to the right here, 2 units to the right and 4 units up. So that's written as vector A is 2, 4. That's a column vector. It's in component form. There's an x component and a y component. To get the size of that vector, its magnitude, that's the length of the line, Pythagoras applies. There's a right angled triangle here, 2 units by 4 units for the shorter sides. So magnitude of vector A is written with these 2 vertical lines on either side, and it's square the components, add and take the square root. 4 and 16, which is 20, root 20, it's a surd, can be simplified, separate videos on that. Root 4 times root 5 is root 20, and root 4 is 2, so it's 2 root 5 when the surd is simplified. That line is 2 root 5 units long. This vector B here, to go from one end to the other, you go to the right, 6 boxes, that's x component, positive 6. 3 units downwards, that's 3 units down in the y direction, that's negative 3. So it's positive 6 for the x, negative 3 for the y. That's components, 6 and negative 3. X component 6, y component negative 3. Using Pythagoras, where you've got a right angled triangle, 6 units by 3 units for the shorter sides. The magnitude of vector B is the square root of 6 squared plus negative 3 squared. Square the negative 3, you'll get a positive 9. It's 36 plus 9, which is 45. Root 45 is root 9 times root 5. Root of 9 is 3, so it's 3 root 5 as a simplified surd. That line is 3 root 5 units long. That's the size of this line, the size of the vector, the length of the line. So that was all in the first video. Now go on to add and subtract. So here's 2 vectors, u and v. U is 5, 1. That means 5 in the x direction, 1 in the y direction. There, for example, is vector u. From one end to the other, you go 5 along in the x direction and 1 in the y direction. Vector v is 2, 3. That's 2 in the x direction, 3 in the y direction. So if we're going to add these together, we go from the end of u a further 2 to the right and 3 up. That's vector v. That's u and v being added. It's like going on a journey. You start here, you move along u. When you get to the end, as you get to the head here, you then follow vector v, 2 to the right, 3 up. So you've gone for vector u 5 to the right, and for vector v 2 to the right. So altogether, from start to finish, you've gone 7 boxes to the right. That's positive 7 on the x direction. In the y direction, you went 1 up for u, and then you went 3 up for v. So that was 1 up for u, and then a further 3 up for v. So altogether, you went 4 up. So when you look at the resultant vector, that is from start to finish, going straight from start to finish is the resultant vector u plus v. That red vector has been 7 to the right and 4 up, which is what you get from the components. If you add the components, you get 5 plus 2 is 7, and you get 1 plus 3 is 4. So the resultant vector can be done in component form very easily, and that's how you do it by diagram. It's called head to tail addition. At the head of u goes the tail of v, and it's just like going on a journey. Now, if you were asked the size of this red vector, that's the magnitude of u plus v, you will find it is less than, individually, the size of u and the size of v added together. So you cannot take magnitudes like magnitude u plus v and split it up. If you want the magnitude of u plus v, you've got to work out the component form here first. 7, 4. That 7, 4 gets used to work out the magnitude. It's no use having the magnitude of u and the magnitude of v. They will not add together to give you the magnitude of u plus v. If you're going on a journey straight from start to finish, that's a much shorter journey than going via some other town. So if you're going on a journey via some other town, that will be a longer journey than going straight from start to finish. So you cannot add magnitudes together. You can add vectors together. You can add vector u and vector v. They can be added, but you can't add magnitudes and get a resultant magnitude. So if you add magnitude u and magnitude v, it will be more than, bigger than the magnitude of u plus v. So when you're asked the magnitude of a vector, you've got to get the component form of that vector first. Don't try to add separate magnitudes. So there's vector A and vector B. That's component form. That's them drawn. Suppose you to add them. You add them head to tail by diagram. You draw vector A. There's a representative vector A. It's just this one up here. Drawn. And from the end of A, that's the head here, you join on B. So you take B and you join it on to the head of A, as if you're going on a journey. There's B added on. That's A and B being added by diagram. From start to finish, from here to here, is the resultant. That black vector is A plus B. Start to finish. Now, what should have happened is, we've gone for A, 5 to the right, and then B's taken us 3 to the left. So for the resultant, having gone 5 to the right, you then go back 3 to the left. You only go 2 to the right overall. And that's what's happened with the black vector here, the resultant. It's 2 to the right. It was 5 to the right, then 3 back to the left. Overall, it's just 2 to the right. And then in the y components, A took you 2 down, and B took you 4 down. So altogether, you should have gone 6 down. And if you look at A plus B, it's going down 6. So that's what you get from the components. 5 to the right, 3 to the left, overall you're 2 to the right. 2 down, another 4 down, overall you're 6 down. So you can add the components. 5 plus negative 3 is 2, negative 2 plus negative 4 is negative 6. With the components, it's very quick and easy. Diagram, just got to be a bit more careful. They join as if you're going on a journey, and head to tail addition. So that's adding by diagram, that's adding by components. You can see that for A plus B here, it's 2 to the right, positive 2, and then 6 down, that's negative 6, just what you get from the components. Here's a subtraction, B minus A. There's A and B again. So take B, there's B, and take the negative of A. So subtracting A is the same as adding the negative of A. That means take A and reverse its arrow. You take A and reverse its arrow, put it onto the end of B, and there's A with the arrow pointing down to the right here, and there's negative A with it pointing up to the left. The arrow head's reversed. So we're now going following the arrows on a journey from start to finish. That's it there. That's B adding negative A. which is the same as b minus a. Component form, there's b, subtract a, it's -3 subtract 5 is -8. -4 subtract -2, that's the same as -4 plus 2, which is -2. That gives the component form. If you check it in the diagram, to go for b minus a, it's -8 on the x direction and -2 on the y direction, just what you get by components. So that's head to tail addition by diagram, as if you're on a journey, and that's using components. What about 3a? Well, that means you can take a and add on a and add on a again. So that's a, that's now 2a, and that's now 3a. Just 3 representatives of a, head to head, head to tail, as if you're on a journey. And that means 3 times we went 5 to the right, and 3 times we went 2 down. So that's 15 to the right and 6 down. In other words, you just multiply the components. So there's a added together 3 times, which is the same as 3a. You simply end up with 3 5s and 3 -2s. In short, you just multiply the components. So 3 times a, 3 times the components. 3 5s, 3 times -2. You're multiplying by a number here. Number just has size, no direction, so we say it's a scalar multiplication because 3 is scalar, it's only got size, not direction. So this is multiplying by a scalar. So the rule, if you want to multiply by a number here outside the brackets, that's a scalar multiplication. Just multiply each of the components. If you have a vector here v, and I was to multiply it by 3, that is join 3 of them together. That's 3 of them joined together. We'll say that's a new vector called u. Vector u is 3 times vector v. Since vector u is 3 times vector v, it's 3 v's put together. These lines must be parallel. When one vector is a multiple of another, the vectors are parallel. So, as a general rule, one vector, a multiple of the other, means you've got parallel vectors. Now if k was a negative number, it'd simply be that one had the direction reversed, but it'd still be parallel. That k can be a fraction, it can be a half, 2/3, 3/4, 7/3, 9/2, -6, it can be positive, negative fractions. As long as one vector is a multiple of another, you have 2 parallel vectors, and therefore you could show lines are parallel. Now, bringing this together, we can multiply by a scalar, like 3a, and we can add and subtract. So let's say by diagram with 3a, so there's a, 2a, 3a, and now 2 b's have to be added on, that is b up here. So to the end of a here, that's it, a's head, we put the tail of b, that's 1b, that's 2b, that's 3a plus 2b, and that's the resultant from start to finish. Now if we check it out by components, 3 times a, 3 5s and 3 times -2, 15, -6, and 2 times b, 2 times -3 and 2 times -4, and now they get added. 15 add -6 is 9, -6 add -8 is -14. The resultant's 9, -14. Just to check it out from this end, we go to the right, 9, that's 9 to the right, and count down, that's 14 down. So the resultant, 9 to the right, 14 down, is component form 9, -14. So that's it done by diagram, you get 9, -14, and that's it done with components. Obviously, we would do it by components as a preference because it's quicker and easier. Now if you're asked the magnitude, the size of that vector, 3a plus 2b, you would just take the components, square add and take the square root. So that's adding vectors and multiplying by a scalar. It's quite straightforward. Here's another example by diagram, 2b minus a. Now what we do, we take 2b and we add negative a. So there's 2b. Take a and reverse its arrow and put it on the end. There's negative of a, so the arrow is reversed. And join up from start to finish. That's the resultant of 2b minus a. We'll check it by components. There's 2 times b. That gives you negative 6, negative 8. And then it's subtract off a here. Negative 6 minus 5, negative 8. Subtract negative 2. So negative 6 minus 5 is negative 11 on the top. Negative 8. Subtract negative 2 is negative 8. Add 2. Negative 6. So negative 11, negative 6. Check it here. That's taking it along here. 11 to the left and 6 down. So that's it, negative 11, negative 6 to go from one end of this line to the other. So that's by diagram, head to tail addition, and that's by components. And this is it summarised. You can add head to tail, like you're going on a journey. We get the resultant vector, or a lot easier, just do it by components. If you're multiplying by a scalar, it's quite easy, just multiply the components. And when you want the magnitude, we had that in the first video. Square the components add and take the square root. So this finishes it by bringing it all together. So everything you've seen is just to get to do this kind of question. Calculate the magnitude of 3u minus 2v. So what you do is you work out 3u minus 2v first. That is 3 times what u is, 2 times what v is, and then subtract. So multiply the components here by 3, multiply the components here by 2, carry out the subtraction of the x components, the y components separately. That is 3u minus 2v in component form, and to get the magnitude, square the components, add and take the square root. 9 and 4, 13, so it's root 13, and it doesn't simplify any further. Apart from 1, there's no square number goes into 13. So you can multiply a vector by a scalar simply by multiplying the components, and you can add and subtract vectors just by adding and subtracting the components. If you click the link in the description, there's a worksheet. It's the same worksheet used in the first video, but from question 6 here on for the second video, in 2 dimensions, there's some vectors given, and you have to simply, in component form, get these resultant vectors like a plus b and so on, 3a minus c. And then, similarly in question 7, working out the magnitudes, you have to do what you did in question 6 first, and simplified the answers with them. So at the end, the answers are there. So it's question 6 and 7 on that worksheet. It's the same worksheet as on the first video, and using the same link, there's a set of notes that covers the first video on component form and magnitude. And this is adding and subtracting and multiplying by a scalar. Hope you found this video useful.